Okay, welcome to our intro to Chapter 7, Ionic Bonding and Metallic Bonding. Thank you, Dr. Conton, as always. Our objectives. We will first talk about valence electrons and how to get these numbers. You already know this. Representative elements, as a quick reminder, are groups 1A through groups 7A. We will talk about the octet rule and how it applies to the formation of metallic and nonmetallic ions. Talk about the formation of cations and the formation of anions. First, let's again define valence electrons. Valence electrons are those in the outermost energy level, and they are responsible for chemical properties. Valence electrons always, in our discussions, will include the s and p electrons in the outer energy level. Please notice that I'm not talking Ds here. We will limit our discussions to s and p valence electrons. These will be considered our highest occupied energy levels. All other electrons that are not valence, so core electrons, are not equal to valence. Every other electron is considered a core electron. Please recall that atoms in the same column, which in our world is called a group, have the same outermost electron configuration, and you've done this several times. Which means if they have the same electron configuration, they have the same valence. The valence, again, is the group number. It's the number, or should I write this? The number preceding the letter A for a representative element. For instance, 2A has 2 valence electrons. Let's do a quick reminder on electron dot configurations. Now they're going to teach it a little differently than I teach it. So we do 1 and 2, 3, 4, 5, 6, 7, 8. Where 1 and 2 represent S and the rest represent P electrons. So we write the symbol. It represents the nucleus and the core electrons, everything except the valence. 1 dot for each valence, 8 maximum. And we don't do this. We change this. We put 2 in the S, then we start the P's. So they're going to do this a little differently than us. Dr. Cotton adds 1 on each side and then doubles up. I don't do it this way. We do nitrogen, S electron, P, P, P. We get the same thing, but we come at it from a different plan. Way back, we learned that noble gases tend to be unreactive because they're stable. Lewis came up with something called the octet rule. And yes, this is where Lewis dot comes from. So he came up with the idea that atoms tend to achieve noble gas configurations, which is 8 in the outer level, except for helium. All the noble gases have 8 in their outermost valence electron shell. Metals are losers, and they're left of stair step, except hydrogen. Not equal to hydrogen. They make positive ions. And let's take a look at sodium. If we look at sodiums, we can see that the loss of this electron will result in a valence shell that is isoelectronic with neon. Electronic. electronic. Calcium, now remember, this isn't how I do calcium, although I'll talk about this more when we're in person with dots. It doesn't really matter for metals, since metals, we'll find this out, are going to transfer or give away electrons. Location of dots isn't super critical because it's going to give away its dots. You can see that it's losing its valence electrons, and we will write it in this format. This is the required format for ions. This particular ion is called the calcium ion. This will get a bit more complicated, but not during this small lecture. Scandium. Now here's scandium, and we can see I'm going to use this. We are going to assume that this is our goal for scandium. Dr. Compton says 2 plus is also a possibility, but we're going to ignore this one and just focus on losing 3. There's this one. Again, we're going to ignore that one, and we're going to focus on losing all 3 of the outer electrons, which would give it a charge of 3 plus. Silver is sort of fun. This is what we predict when you were little kids, what the electron for silver would be. But we know that we don't ever have a D9. So we rob one from we promote an electron from the S to the D, and then we can see that our electron that we want to lose is that 5s, which will give us a 1 plus ion. So silver will always have a 1 plus ion. Silver still doesn't have a noble gas. It's not a true noble gas. We call that best it can do, but not a noble gas, a pseudo-noble gas configuration. And these are often D10. Anions, of course, gain electrons, will make negative ions. For instance, let's look at sulfur, and this is one you did on your periodic table packet. Has 6 valence electrons. We want to go to 8. So adding that 6th electron will result in 2 excess electrons, which gives us a 2 negative charge. Halide, which we've also discussed, are ions formed from halogens. Nonmetals writing electron dots will have more electrons. They usually have 5 or more. So here's phosphorus, 1, 2, 3, 4, 5. We can see that we need 3 electrons. Oh, I forgot to turn off my sound on this. So that's the phosphide ion, and it should show the ions. I often represent these with brackets, so you might see mine with brackets. So what do we know? All atoms try to reach a noble gas configuration, and there's a stable argon because this has a stable octet. Noble gases have their 2s and 2p, except helium has just 1s2. 8 valence electrons, stable. That is the octet rule. 8 in the outer shell has a particularly high stability. And we're done.